Hello, Young Math Padawans. It's Mrs. Angel, and welcome back to our Solving Quadratics Vertex Form lesson, Part 2, applying the square root property of equality to actually solve quadratics in this form. Now that we've used the square root of property a few times, we are ready to solve some quadratics. So grab some notes and let's get started. So in our first example, x squared minus 9 equals 40. The first step that we're going to do is identify where the power is in this function, because we need to isolate that power, that square, before we can actually apply the square root property of equality. So it's pretty simple to see that the power here is x squared. So our goal is to get that pink circle by itself before we actually apply that property of equality. So how do we do that? Well, first we're going to apply our addition property of equality and add 9 to both sides, just as if we were trying to isolate x. The only difference now is that we're isolating an x squared. So after we add 9 to both sides, we're left with x squared equals 49, and our power, or our square, is now isolated. How do we undo a square? Well, we apply the square root property of equality, and we take the square root of both sides. As we recall, there are two square roots of 49. One of them is positive 7, and the other one is negative 7. And at this point, there is no additional solving that we have to do. All that's left is the check. Starting with positive 7. 7 squared minus 9 equals 40. 49 minus 9 equals 40. And 40 equals 40. Meaning that 7 is indeed a solution. So negative 7 squared minus 9 equals 40. That's 49 minus 9 equals 40. And since 40 equals 40, then negative 7 is also a solution. So what does all of this mean? It means that this quadratic has two zeros, and they are 7, 0 and negative 7, 0. So imagine a parabola opening upwards, crossing the x-axis at these 2 points. So example 2, the function is quantity v minus 3 squared plus 3 equals 3. Step 1, identify the power or the square that we need to isolate. In this case, our power happens to have a base that is a group. That doesn't matter. If you need to, imagine that this were one big variable x or something. Don't worry about the fact that it has a group. That is a power, and we need to isolate that power so that we can undo the square with our square root property. So how are we going to do that? Well, we're going to apply the subtraction property of equality and subtract 3 from both sides. That would leave us with quantity v minus 3 squared equals 0. So now that the power is isolated, how do we undo a square? By applying the square root property of equality. Now, as we recall, there's something special about 0. 0 only has one square root, which means we're only going to set up one equation here. The square root of v minus 3 squared is v minus 3, and the square root of 0 is 0. So after some quick solving, we only end up with one solution, v equals 3, that now we're going to check. So here we go. 3 minus 3 squared plus 3 equals 3. 0 squared plus 3 equals 3. 0 plus 3 equals 3, and 3 equals 3. So it does appear that 3 is a solution here. So what does all of this mean? It means that this quadratic only has one 0, and that 0 is sitting at 3. So imagine a parabola where the vertex happens to be sitting on the x-axis, opening upward. Example number 3 is a little more complicated, but our steps remain the same. We have 3x squared plus 9 equals 84, and our first step is to identify just the power. The power here is our x squared. So our goal is to isolate that x squared just as we would if we were isolating x. So first I'm going to apply the subtraction property of equality, creating a 0 term out of that 9, and that gives me 3x squared equals 75. The power is still not fully isolated. So from here, I will apply the division property of equality. And now I'm left with x squared equals 25. The power has now been isolated. So how do we undo a square? We apply the square root property of equality. And 25 has two square roots. One of them is positive 5, and the other negative 5, which means we have two solutions to check. Starting with x equals 5.
3 times 5 squared plus 9 equals 84. That's 3 times 25 plus 9 equals 84. That's 75 plus 9 equals 84. And 84 equals 84.
Meaning that 5 is indeed a solution. On to negative 5.
3 times negative 5 squared plus 9 equals 84. Again, that's 3 times 25 plus 9 equals 84. 75 plus 9 equals 84. And 84 equals 84.
Showing that negative 5 is also a solution. So what does all of this mean? This quadratic has two zeros. They are 5, 0 and negative 5, 0. So imagine a parabola crossing the x-axis at both of these points. Final example in our video, 6 times, this is a lot. Let me write it out. We have 6 times quantity n plus 2 squared minus 1 equals 53. So let's start by just identifying the power. The power here is n plus 2 squared. Don't worry about the fact that it has a group. Just imagine that to be a power with a variable base. Our goal is to isolate that power. So let's start off by adding 1 to both sides, because that will at least create a 0 term there. And that leaves us with 6 times our power equals 54. Our power is still not fully isolated. We need to get that square by itself. So my next step will be to divide both sides by 6, because that creates a big 1. And now I have my power n plus 2 squared equal to 54 divided by 6 is 9. So now that the power is isolated, I can come in and undo that power, undo that square by using the square root property of equality. Now 9 has two square roots. It has positive 3 and negative 3. So from here, I'm going to set up two equations, one where n plus 2 equals positive 3, and one where n plus 2 equals negative 3, and solve. Subtract 2 from both sides. Subtract 2 from both sides. And we have n equals 1 and n equals negative 5. So it would appear that this quadratic has two solutions. Let's go ahead and check. Starting with n equals 1, 53, and yes, 53 equals 53, showing that n equals 1 is a solution. Let's try n equals negative 5. Minus 1 equals 53, and yes, 53 equals 53. So what does all of this mean? It means that this quadratic has two zeros, and they are 1, 0, and negative 5, 0. So imagine a parabola crossing at those two x-intercepts. That's it for today's lesson. I will see you next time.